Okay, so what we usually care about is we care about how much is this energy hitting the Earth. So this energy, right, is being spread out. We've calculated the power, but we want to know the intensity of the light on the surface of the Earth. So this energy that we've calculated using this equation, right, the E is dropped because it's 1, we found that the power was this amount, and all that power, all that energy is going out, and it's not all going straight to the Earth. Not all of it is going to the Earth. It's actually spreading out in all directions. So it's going out everywhere. Only some of that is ending to the Earth. So if we want to know how much is hitting the Earth, we should calculate the intensity, right? So we can know the power per unit area because it's spreading out. So in order to do that, the trick is we need to get the power in the area. The power is easy. We've just did that. So we take this number, plug it in there for the power. The question is what do we do to find the area? Do we do the area of the Earth? No, we shouldn't. But that's because if we were doing the area of the Earth and we took all this power, that would be like we're saying all of this energy ends up on the surface area of the Earth. It doesn't. It goes everywhere along this area. So what we're doing is we're taking all this energy and we're spreading it around the area of this circle. This, actually, it's not a circle. It's a giant sphere. Okay, so this sphere here, it's spreading out all along. And the intensity here, where the Earth is, should be the same as the intensity here, and the intensity here, and the intensity here. We're taking all that energy and we're spreading it out along the surface area of that sphere. So the surface area, this area here that we're going to plug in, should be the area of this sphere, which means we need the radius from here to here, or in other words, the distance from the sun to the Earth. Okay? The intensity on the surface of the Earth should be greater than the intensity on the surface of, let's say this is Mars. This is because even though the same amount of energy is being sent in all directions, the energy is being spread out along a larger surface area for Mars because it's farther away. This is just like when we shine a light, right, the flashlight onto a piece of paper when it's close versus far away, right? That light will spread out more when it gets to the area where Mars is. Okay, so the light will be less intense. So we're going to quickly calculate what is the, oh, sorry, I forgot this. So how do we calculate the area? Don't forget it's 4 pi r squared, and then the radius is just the distance from the sun to whatever planet. Okay, so if we want to quickly, we're going to quickly calculate the intensity of the light on the surface of the Earth and on the surface of Mars. So we can use this information. You can pause it and calculate. Once you do, you will find that the intensity on Earth, right, is going to be as follows. We take the same power, plug it in. We're going to use the radius, meaning the distance from the sun to the Earth, plug it in, do all our math, and we get 1,361 watts per square meter. That means that there is 1,361 joules of energy hitting the Earth every single second per square meter. So this isn't just this isn't the total energy hitting the Earth. This is how much energy is hitting the Earth every second for just a square meter worth of area. Right? There's actually a lot more energy hitting the Earth because the Earth is very large. This is the intensity or area or power per unit area. Okay, so let's actually calculate then the answer for Mars. We get 579 watts per square meter. And we can see it's obviously smaller. Even though the radius isn't twice as big, the intensity is pretty much half the size. And that's because in the equation, right, 4 pi r squared, right, the radius has a big effect because this is area we're talking about. So light is coming in and hitting the Earth. Some of it is absorbed, that light energy, some of that energy is absorbed, and some of it is reflected because the Earth is not a black body, right? We've already looked at that. So that means that some is reflected out. Notice these arrows are thinner. That's because some is absorbed, some is reflected out. Now what this has to do with is a term called albedo. Albedo is the ratio of energy that is reflected versus the incident, okay? Or mathematically, that would be the albedo, or alpha, is the total energy that is reflected / scattered divided by the total power, right? Or incident power. Okay, so we can figure out the albedo, okay, by just calculating the different amounts of, or the energy that is reflected versus the energy that comes in. However, there are different factors that affect the Earth's albedo. Okay, there is the season. For example, in winter, right, there's more snow and ice, and therefore the Earth will reflect more light then it will absorb. Okay. Also, other things might affect, like the temperature. Similarly, the temperature might affect the amount that the atmosphere will reflect, because of at different temperatures it might behave differently. Also, cloud cover can also affect the Earth's albedo as well. White clouds are white, and white is something. When something is white, it will reflect all of the colors. That's what makes it look white. And so, cloud cover being white will reflect more light. Okay, the Earth's actual mean albedo is about 0.3. That means it's about 30% of the incident radiation is reflected. 30% of whatever hits the Earth is sent back out. Okay, now you are given this equation for albedo on your yellow packet. You are not given this equation here, and you need to memorize it. Sorry about the box, it's off center, but you need to memorize that the albedo of the Earth is 0.3, or about 30%. It's just a good random fact. Okay, energy, once it hits the Earth and it's absorbed, so the other remaining 70% that hits the Earth is absorbed, where does that energy go? Well, it is absorbed. Before it was absorbed, it was in the form of wave energy, or in other words, electromagnetic radiation. After it's been absorbed, just like when you sit out in the sun and light hits you and then you absorb the light, you warm up, right? So that energy turns into heat. Now that heat will rise the temperature of the Earth, and we can calculate the rise of temperature of the Earth with an equation. We've already seen this equation, right? The equation that relates change in temperature with heat. The equation was Q is equal to mc delta T. This equation is going to be very similar to Q is equal to mc delta T, but ever so slightly different. It's Q is equal to Q is equal to AC delta T instead of M. So you drop the M and replace it with A, because you're not really going to heat up the entire Earth from the sun. The sun will give the Earth energy, but it will not heat it all the way down to the center of its core. Okay, it really only heats the surface. So we're going to use this equation, Q is equal to AC delta T, where A is the surface area of the Earth. Okay, and C is very similar to C in our Q is equal to mc delta T equation, is like specific heat, which is what C was before, but instead we call it surface heat capacity. Okay, and surface heat capacity is where, specific heat capacity with the Q is equal to mc delta T was the amount of heat used per unit, the amount of heat required to raise 1 degree of temperature for every unit of mass. Okay, that's what specific heat was. Surface heat is now going to be the amount of heat required to raise 1 degree of temperature per unit of area, or per square meter. That's what surface heat capacity will be. Now they actually give you this equation on your IB data booklet. So it's basically Q is equal to mc delta T, but they put it in a little weird form, right? They write it in terms of the surface heat capacity, and you can still use it. Now, if the Earth absorbs energy, it will warm up. However, the Earth is always absorbing energy because the sun is always shining on it. So the Earth will continually absorb energy after energy after energy, which means technically the Earth should get hotter and hotter and hotter and hotter and never stop getting hotter. It'll forever get hotter, and eventually we will all become baked chickens. However, it doesn't do this. We know it doesn't do this. The Earth's temperature stays relatively constant. Sure, it fluctuates from season to season, but year to year it stays relatively constant. Okay, that's because heat, or as the Earth absorbs energy, the Earth has to get rid of some of that energy in order to maintain the same temperature. Okay, so as the Earth absorbs energy in the form of electromagnetic radiation, right? The sun sends light to the Earth. So here's the sun, here's the Earth. Sun sends light to the Earth in the form of all the spectrums, right? It's in electromagnetic and infrared, light, microwaves, and gamma rays and X-rays, and all those different rays, sends it to the Earth. The Earth absorbs it and then spits it back out. Remember, you do not need to be a black body to emit electromagnetic radiation. However, since the Earth is relatively cool, it's one of these down here, right? It's relatively cool. Then the amount of, or the spectrum that it's emitting is in the infrared. Okay, so as it absorbs energy in all the spectrums, it emits the energy specifically in the spectrum of infrared. Now this is going to be really important for what we're doing. So compared to the amount of energy absorbed, how much energy should it radiate back out if you want it to stay at a constant temperature? The two should be the same if you do not want your overall temperature to increase. Now granted, it will absorb more than it spits out during the summer when it does get hotter, and during the winter it does spit out or radiate out more than it absorbs, and that's why it cools down. But overall, in general, as a general average, it should be the same if you're going to keep the average temperature the same. So here's a picture of what the graph, or what like the energy is doing if you had no atmosphere. So for example, Mars has no atmosphere, so if this was Mars, right, energy comes in. I believe the intensity was something like 580 or something watts per square meter. So as energy comes in, some of it is reflected out, right? You can calculate the amount that is reflected out by using the albedo. Remember, the albedo is the percentage that is reflected. So if you take that percentage and multiply it by the intensity, or in other words, alpha I, this would equal the amount of light that is reflected. Now, the other amount, some of it's reflected, some of it is received. So the other amount that's not reflected would be absorbed into the earth. So the total amount being absorbed would be the original amount, I, minus whatever is reflected. So it would be the intensity minus the reflected amount, or alpha, or albedo, times I. Now, how much, therefore, should be emitted if it's going to remain at a constant temperature? So if it's going to remain at a constant temperature, it's got to spit out as much as it receives, right? So that means the amount radiated is also I minus alpha I. And that is kind of a quick way to look at how much energy, right, is coming in versus coming out. And the amount coming out should equal the amount coming in if it's going to stay at a constant temperature. However, the Earth stays, or does have an atmosphere, so let's look and see what it looks like with an atmosphere. With an atmosphere, very similarly, energy comes in, some is reflected out, and then it spits back out. However, the atmosphere acts like a giant blanket that ends up taking some of that light and reflecting it back down. Okay, it absorbs it and spits it out back down, re-radiates it out. However, I don't want you guys to think that it will absorb the incoming light. Well, it does somewhat, but it shouldn't just absorb the incoming light and spit that back out. It only absorbs the stuff trying to escape. And the reason is because our atmosphere is made out of certain elements that will absorb specifically infrared light, but not other wavelengths. So the sun, which is way up here, right, and shining light down to the earth, is shining, remember, light in all of its spectrums. So it's shining electromagnetic waves in the form of light, infrared, ultraviolet, radio waves, microwaves, right, all of these different ones. And so a lot of them are getting through because the atmosphere doesn't touch these other wavelengths. It only worries about infrared. That's the main one that it will affect. So the lights, because they're not all infrared from the sun, will come in, get to the earth will absorb this light. Then it spits it back out in the form of infrared. Remember, because the earth is kind of cool. So it spits it out in infrared, and because it's now infrared being spit out, the atmosphere will start to absorb some of that and re-radiate some of it back. Some of it gets spit out while some of it comes back. As a result, the earth will be slightly warmer, well, actually quite a bit warmer, with the atmosphere than it is without. It will still be able to come to a constant temperature, so the total amount radiated outward should in the end equal the amount sent inward. However, the total amount kept inside the system should be higher than with the atmosphere than without. It's kind of like standing in the cold without a blanket, right? Eventually your body will come to a specific temperature and it'll stay at that temperature as your body tries to produce heat and you lose heat at the same rate. But you're going to be quite cold. Or standing in the cold with a blanket, and so you will also come to a certain temperature where heat will escape as quickly as you can produce the heat. However, it will be a much warmer temperature, right? The atmosphere acts as a blanket. This result, or this effect, is known as the greenhouse effect, okay, is what it's called. And we're going to learn exactly what that is. So here's another picture of what this might be happening. This is a cool Sankey diagram of what's happening, right? So the energy comes in from the Earth, right? Maybe 342 comes in from the Earth. So this is incoming solar radiation. They've representing as 342 watts per square meter. Coming in, some of it is reflected by clouds, right? Some of it is reflected off the surface of the Earth. This is all the reflected stuff because of the albedo, right? Some of it is even absorbed into the atmosphere because some of it's still infrared. But a lot of it still gets through and is absorbed by the surface. When it spits it back out, though, it spits it back out in the form of infrared. So it spits it out, okay, and it spits it out towards the Earth. However, a lot of it's radiated back down, and so there's a bunch just bouncing around in here. In the end, though, the same amount that comes in will be the same amount total that leaves. Okay, the greenhouse effect, if we were to summarize it and we were to explain it, these would be the key summary points that you should keep in your notes. So, the greenhouse effect is the warming of the Earth caused by the following. So, radiation from all spectrums enter the atmosphere and is absorbed by the Earth. So it'll get through that atmosphere and it'll be absorbed by the Earth. Then the Earth re-emits that radiation or that energy in the form of infrared. Then infrared specifically will be absorbed by certain gases in the atmosphere, and then those gases will then re-emit that energy out or re-radiate it out, some of it back towards the Earth and some of it out. But as a result, it keeps that energy inside the Earth system and keeps it warmer. So this is an example or an explanation of the greenhouse effect, which you should be able to explain on a test. So there are different compounds that act as greenhouse gases and absorb this infrared radiation and radiate it back. One of them is water vapor. Carbon dioxide is one, and one of the ones that we are most familiar with. Methane gas is also one. Nitrous oxide and ozone are also some as well. So the reason why these gases absorb certain wavelengths, specifically infrared type wavelengths, but not others, is because molecules can act like masses on springs. If you'll remember right from our simple harmonic motion unit, when we took a mass on a spring and we let it wiggle, that mass liked to wiggle at a very specific frequency. In other words, it had a very specific natural frequency that it would vibrate at. Well, molecules kind of behave like masses on springs. For example, if you had O2, which are two oxygen atoms, those two oxygen atoms are bonded together. So it's like this, here's an oxygen atom, here's an oxygen atom, and they are attached to a spring, and they're just going to wiggle back and forth. The more energy they have, the more they wiggle. And they also have certain natural frequencies that they will respond to. According to which frequencies they like or that they will respond to determines which wavelengths or which frequencies of electromagnetic radiation they'll actually absorb. If the two match, it'll be able to absorb it. If not, it won't. Kind of like, when you push the kid on a swing at the right frequency, the kid swung higher and higher. If you push it at the wrong frequency, the kid wouldn't. This is a factor known as resonance. Okay, so similarly, the molecules will resonate with certain frequencies but not with others. Okay, the graphs here actually demonstrate this idea that certain gases or compounds will absorb certain wavelengths or frequencies of this electromagnetic radiation, but not others. This graph you should be familiar with. You don't need to memorize it, but the concept of what this graph is saying should be familiar. This is actually lots of graphs. Here's one graph, here's another graph, here's another graph. Okay, so the graphs are the x-axis are the wavelengths, okay, which can be related to the frequency. So the wavelengths of the electromagnetic spectrum, most of these shown here are all in the infrared. Okay, and then this y-axis is the absorptivity, or in other words, when it's high at 1, it's absorbing 100%. If it's low at 0, it's not absorbing any of it. So for example, if we come up here, methane, at this wavelength over here, it's not really absorbing anything. Neither this wavelength here, or this wavelength, or this wavelength, or any of these wavelengths, up until this point, where all of a sudden, at this particular wavelength, whatever that is, all of a sudden spikes way up, and that's because it'll absorb that particular wavelength. That is one of its natural frequencies, and it'll respond, okay? It also kind of absorbs these, not really, but then it really absorbs this one as well, okay? So then we see on the nitrous oxide, very similar pattern, like little tiny spikes here, and then a big spike here, and then nothing, and then a big spike, right? And so, it'll absorb some frequencies, but not others. Oxygen, right, has a big swath over here. So there's actually quite a few that oxygen and ozone will absorb, and then a couple of little spikes. Carbon dioxide, you'll notice these are some pretty wide peaks, and there's another little swath over here. So there are quite a bit of different wavelengths carbon dioxide will absorb. The biggest factor is probably water vapor, right? Look at the width of all these different wavelengths it can absorb. It can absorb a lot of different wavelengths, and when they absorb it, right, they spit it back out and radiate back down towards the Earth. So this last one would be all of them added together, and you can see you've covered quite a few of the infrared spectrum. Now a very similar graph, but that is backwards, and I've also seen this kind of graph just appear on the test, where and you just need to be familiar with both of them, right? So instead of showing you the wavelength and absorptivity, it's showing you wavelength and transmittance. So it's exactly backwards. So instead of each spike representing how much, or that it will actually absorb that energy, each spike is showing what it will allow to transmit through without absorbing, right? So these are just the ones that it will allow through and not the ones that it absorbs. Absorbing would be the ones that have zero transmittance. So this particular wavelength, right, water vapor absorbs quite well. Okay, let's find a particular spike, right? CO2 and nitrous oxide, right? There's a spike right here that shows that it will absorb it because of these two gases, right? So this is a transmittance one instead of absorptivity. You could see a graph with either one. Okay, so we have learned how to calculate the power coming off, or the energy coming off of the sun. We've learned how to calculate the intensity of sunlight on the surface of the Earth by the time it gets out that far. And we have learned we've learned the equation as shown here that will allow us to take that energy and figure out how much heat, or how much the surface of the Earth will increase its temperature. However, this does not have intensity in it. So how do we get to intensity to actually changing temperature? And it's easy to do, but we just got to do a little bit of math, and they actually, since you're going to do the same math every time, they've actually derived a new equation for temperature change in terms of intensity. So I'm going to just quickly derive that real fast. Okay, so the following, we're just going to rearrange this original equation so that we're solving for change in temperature, and we get this. We're going to rearrange this equation by doing algebra, right? Q over AC is the same as Q over A times 1 over C. Okay, so it's just algebraically, this is the same thing. Now we will make note that intensity is power per unit area. Remember, power is change in energy, or work per unit time. So intensity is also equal to energy divided by time times area. Okay, so over here, that's similar to heat over area, except this is, because heat is energy, right? So this is energy over area, and time is on the bottom. This is just energy over area. So we got to get time in the equation so we can get intensity in here as well. So what we're going to do is we are going to divide by time, the whole equation by time, so that time is now down here. And we're also going to multiply by time, so time is on top. So that way we don't have to worry about, or so that way we haven't actually changed the equation at all. When you multiply by a number and divide by a number, it's not going to change anything overall. Now we can take all this stuff right here and we can replace intensity in there. However, since this right here, since heat is actually the change in energy, right, not just energy, this will actually be the change in intensity. So we plug that in here and we get change in intensity is equal to change in time divided by CS, and that equals our change in temperature. Or we can rearrange and we finally get the equation. Change in temperature is equal to your change in intensity written out this way. So it's, in other words, your intensity in, meaning the stuff you absorb, minus intensity out, meaning the stuff you emit out, right? So that's how much your change in intensity would be, because you're absorbing some and then you're spitting it back out, right? So change in temperature is equal to intensity in minus intensity out, all times the amount of time, how long it's been absorbing for, divided by CS, which is, again, the surface heat capacity. This equation is also found in your IB data booklet. You just need to know what the variables are, what they represent, and what to do with them, and how to calculate it. So just a quick check-in. What happens when the amount of energy that leaves the Earth is slightly less than the amount that is incident on the Earth? The answer, it'll warm up, right? So you're absorbing more than you're spitting back out, and it'll warm up. So when intensity in is greater than intensity out, the Earth is going to get warmer. When can this happen? Because remember, we want the Earth to stay at a relatively constant temperature. Well, this does happen. This happens on a seasonal basis. Every time it hits summer, the intensity in is greater than the intensity out, and the Earth warms up. Then it hits winter, and the intensity out is greater than the intensity in. So it's emitting more than it's receiving. And so then the Earth cools off, right? So this actually does happen very often every year, okay? On average, though, we want the two to be the same, so the temperature of the Earth stays relatively constant. However, it's not necessarily going to be the same. We will still gain heat or lose heat, or we have been as a large trend, and that's what we're talking about, and that's what we're calling global climate change.